As we previously saw, the memory structure of a modern computer looks like this, where we have a memory hierarchy. Now the question is, can we model this memory hierarchy in using theoretical ways in some way, such that we could design algorithms for this model and analyze them with the hope that this model could lead to a more realistic model of the computers. One way to do it, of course, is to introduce one parameter for each of the components involved. We could have one parameter to denote the number of cores, parameter to denote the size and the latency of the L1 cache, L2 cache, and etc. The problem is that we will end up with many different parameters, and it will be very difficult to analyze algorithms and to even compare different algorithms that depend on so many different parameters. An alternative idea came a few years ago, and it's known as the cache oblivious model. So in this model, you design the algorithms for just a simple model of the computer that involves a processor and a memory. So the algorithm does not use the memory size. The algorithm does not use any extra parameters. However, when we analyze this algorithm, we analyze the algorithm in the IO model. In other words, when we try to estimate its number of cache faults or number of blocks that the algorithm reads, we assume that we have a memory of size M, and the transfer of the element from the disk to the memory takes size B. Since this M and B are not used in the algorithm, the analysis could be applied to any combination of M and Bs. In particular, it could be applied to any two levels in the cache hierarchy. For instance, if you go back to the previous picture, it is assumed that the algorithm just accesses some elements in the memory without knowing anything about the cache sizes. And in fact, this is what we do in practice as well. We do not on purpose encode the sizes of the caches in the code that we implement. However, if we could analyze the caching behavior, let's say with respect to the memory and the cache size, in which the cache size, the L3 cache, behaves as a memory of size M, and the memory behaves as a disks, if we could show that the number of cache misses between these two components is small or is optimal, then this analysis could be applied for any two levels of the hierarchy. So it could be applied with respect to L2 and L3, it could apply between L2 and memory, and so on. The only assumption involved here is that we assume some optimal caching replacement behavior. What this means is that we assume that the entity that models or that controls the behavior of the cache actually knows what is the best strategy with respect to future cache requests. This might seem a bit unrealistic, but the known heuristics approximate the best possible behavior of the cache up to our constant factors. So therefore, from a theoretical point of view, we could assume that the cache behaves as an optimal cache. And if we assume this, then the analysis follows, and it shows and the optimality on one level of caching implies optimality on all of the level of caching.